Good morning, ladies and gentlemen. This is regarding online education system, SWAYAM course, online course, which is basically online course to be developed by jointly Ministry of HRD and NIT Durgapur for chemical engineering course material. Myself, as you see that Sapan Pudua from Department of Chemical Engineering, NIT Durgapur. One module I have been asked to develop, which is basically your Prius Law of heat conduction and cell energy balance, and this is one of the fundamental part of this heat transfer problem, and this transport phenomena approach is basically which has been very nicely brought out by the Barr, Stewart and Lightfoot transport phenomena. This three gentlemen is basically the big guys from University of Wisconsin who wrote this such nice book, and it has been used by this three, not only for chemical engineering, for mechanical, this metallurgical engineering, other disciplines. So, this book is very unique in the sense that the generic approach is nicely written over there. So, I took a lot of materials from this book only. So, now let me get into this course material that I have developed. Here first things that we have to do, that what is the objective of this particular module, this the Prius Law and cell balance, which is basically that to understand the connection between the molecular transport and your kinetic theory molecules, because that conduction or Prius Law, which is basically relying on that that molecular transport and obviously that kinetic theory of molecules, and that we will illustrate later. Next objective is to demonstrate the cell balance of heat transfer in a micro channel, and I will illustrate why I have taken this particular example. There is some immense importance of this particular example in a practical application. Next thing is to show the effect of shear force or viscosity on the thermal boundary layer. So, these are the three objectives that we are going to meet by this course, by this module. Next thing is that your before I take up this Prius Law of heat conduction, which is basically the combination of molecular transport and kinetic theory of molecules. Before that, we should know what is the primary things that we should know before this thing. Like one thing that that this is the unified theory of molecular transport. Molecular transport is basically the conduction of this momentum, heat and mass, and that purely relies on that molecular motion. Molecular motion means that even there is no bulk flow, there is no velocity of the molecules, molecular itself moves on that basis of that kinetic theory of molecules, and there is the three parts, three components are there. One is the rotational motion, another is your translational motion, and the last one is that vibrational. So, three molecular motions are there. Even there is no bulk flow, that molecular motion is responsible to transfer that this momentum, heat and mass from higher region to lower region. I mean that momentum of heat, mass and momentum, and they will go down from they will transfer from downhill trend, which is basically the from a region of high velocity, high temperature and concentration to a region of low velocity, temperature and concentration. So, all these three quantity they have the transfer direction from high region to lower region. So, this is a generic approach that that can be applicable to your momentum, heat and mass transfer. So, next thing that another unified part of the unified theory is basically that flux of momentum, heat and mass is proportional to that driving force, which is basically the called the transport law, and this unified theory is applicable to any of them, any of the transfer like momentum, heat and mass. And when we are putting this proportional to driving force, which is basically that constant, that proportionality constant is known that the transport properties. I mean, the next line is saying that this proportionality constant of this particular relation is giving the estimate of transport properties, which is basically the viscosity might be in the case of the momentum transfer, thermal conductivity, which is basically for the heat transfer, and the mass diffusivity, which is basically for the heat mass transfer. So, and last one is basically that which is called the direct. It is basically that this molecular transport is basically the direct can you repeat this part?
Yes sir, yes sir, you
okay.
Continue sir.
I will continue?
Yeah.
Okay. So, so this is this molecular transport is basically the direct consequence of kinetic theory of molecules, which is basic, which is more prevalent in the in liquid molecules, vapor molecules and gas molecules, right. Next thing is that now I try to switch to Fourier's law of heat conduction. As you see that the transport law that it flux is proportional to the driving force. In the case of heat conduction, the heat flux will be through the medium of by conduction, which is basically the molecular transport, is proportional to the temperature gradient, and temperature gradient is the driving force, and the area through which that heat flow is taking place is basically the always the normal to the heat flow direction. Next thing that if this Fourier law of heat conduction is any of the as I said previously that any of the transport law is used to find the transport properties like thermal conductivity. So, we can apply this Fourier law for heat conduction to find out the thermal conductivity experimentally. This thermal conductivity of the medium or thermal diffusivity, whatever you say, that for solid, liquid, gas, vapor by measuring the heat flux and driving force. Heat flux we can measure, as you know that energy meter that there is the watt meter is there, we can measure the heat flux, and temperature gradient, temperature sensor you are putting across the wall, or maybe that across the bar, then you can find out the temperature gradient. So, by putting that the Fourier's law, you can experimentally find the thermal conductivity. That is the one of the basic use of that Fourier's law of heat conduction. Next thing I should take up this that so Fourier's law, as you see that it can be applicable to any of the medium like solid, liquid, gas, vapor, whatever it is. In the case of liquid, there is some kind of modification we can have, like it cannot be directly it is very difficult to apply Fourier's law directly to find the thermal conductivity in the case of liquid or solid. sorry, that too has to be repeat.
Yes, sir. You continue, sir.
Okay.
Sir, the mistakes when it will happen, you continue it, sir.
Okay.
You will edit this all parts, sir.
Okay, okay, that's fine. Then it's fine. Okay, so so unlike the case of solid, for case of liquid, we can do this apply. We can apply the Fourier law in combination with that kinetic theory of molecules. That basically that both can be combined together to find out that that thermal conductivity. Like in the previous case of solid, we can find that thermal conductivity by applying only the Fourier law, but in case of liquid and gas or vapor, whatever it is, in that case we have to apply both kinetic theory of molecules and your Fourier law to find out the thermal conductivity. Now, one of the very known theory is that that eye-ring theory that has been used that are being used extensively to find out the thermal conductivity of liquid. Here as you see that like in this bar is basically, oh, it is going back. Okay. So, as you see that N bar which is basically the number of molecules per mole, and this V bar is basically that which is basically volume per mole, and Vs is that that sound velocity, and by this combination we can find that thermal conductivity of liquid. Here you see that sound of velocity, that gamma is the that specific heat ratio, which is basically 1 for that vapor and liquid, and as you see that del P by del rho, which is basically the can be estimated from equation of state. So, that compressibility we can estimate from the equation of state. Any of the equation that are available, van der Waals equation can be used, maybe that SRK equation can be used, maybe the RK equation can be used. All these equation can be used to find out that compressibility, which is basically that this derivative. So, that can be used. Next thing that for gas molecule we can use this Chapman-Skunk theory. Chapman-Skunk theory is known, very known, well known theory, which is called the monoatomic vapors and gas, and this theory is, has on the right hand side the temperature, your the molecular weight m, and the sigma is your that collision diameter, which is the part of the the kinetic theory of molecules, and collision function also, which is basically the kinetic energy function of kinetic k T by epsilon, which is basically that kinetic energy component. K is the Boltzmann constant as you see, and epsilon is your like that characteristic energy. So, this equation being used for the calculating the thermal conductivity or for estimating the thermal conductivity for vapor and gases. You will find another thing that although this monoatomic vapors and gas are being used, there is some kind of limitation of you cannot use this theory for for what you call polyatomic molecules or polyatomic gas. For this case we have another thing that you see that Bromley 1952, Bromley is from one big researcher in boiling, he is from University of California, and there is a unique you can that they empirically proposed certain equation. Here we have the Eucken formula, which is depending that thermal conductivity is depending on R by M and specific heat capacity, and from which we can also calculate that Prandtl number. Prandtl number is one of the thermal properties that we use for calculating the heat transfer coefficient. So, these are the all about the thermal conductivity for your solid, liquid and vapor medium. Now, I should switch to this cell balance, which is a very interesting part of the transport phenomena approach, deriving on energy equation. As you see that based on the description of the physical description of the problem, or based on the understanding of the system, any of the system, chemical engineering system might be mechanical or nuclear, whatever it is. So, that system might be understood very clearly. Based on that understanding, we have to derive the equation, model equation. That model equation is useful to diagnose the system subsequently. Here, this cell balance is basically the fundamental approach, which is the unique approach of transport phenomena. We can use this approach to derive this balance equation, energy balance equation, particularly by using the law of conservation principle. And we are using, we will show this case study also, that how to do that in a cell energy balance in micro channel. Micro channel is very important part of our that I will tell later. And next thing that this in the cell is basically the kind of control volume, whose surface will be always the normal to the flow of heat, that is and here that principle of cell energy balance will show through an example that is called, that I said previously, that heat transfer problem in the micro channel. Here you see that this micro channel is basically very important part in which we will demonstrate the effect of velocity profile on Nusselt number for heat transfer in a narrow slit. This narrow slit, or what you call the micro channel. That micro channel has a huge application in our particular the work what we are doing right now, that bubble growth and collapse, boiling heat transfer and associated boiling stabilities in the micro channel. And there this particular micro channel two phase heat exchanger is has a practical impact. Also two phase micro reactor, that is also one important part in the chemical engineering, where we use that micro channel. And next thing, the last part is that whenever there is a enhanced boiling we need, we use the micro channel to expedite the formation of micro bubbles. Micro bubbles always withdraws the heat or removes the heat from the surface, hot surface, like in the from the nuclear surface, nuclear fuel pin, that or maybe that hot plate, that micro bubble formation always removes huge amount of heat, and there we use that micro channel. So, this is this problem is has a lot of practical impact. Now, to show the things how we do the cell balance, here this I should refer this once again, that Barr Stuart Lightfoot book, where this problem has been taken up, from which this problem has been taken, which is basically the combination of forced convection of heat and that the flow in the slit, and the problem number 2E2 in this book, particular book, and convection of heat there in the section in 9.8. And I have combined these two problem together to find out the one impact or on consequence, that what is the effect of velocity profile on the Nusselt number when there is a flow of in the micro channel or narrow slit. Here if you look at that diagram, So, regarding the cell balance, as you see in the figure, this schematic in figure A, that blue two blue bar is there, there is the wall of the that slit, and this center line is the x equal to 0, and as you see that x direction, z direction flow is there, and there is two boundary condition, as you see that three boundary condition, this t 0 at the z equal to 0, and if you look at that two boundary condition for x equal to minus b and x equal to plus b. I will look at why this boundary condition has come up, because it depends on that this equation, types of equation. And as I said that this water is flowing along z direction, and this boundary condition is saying that we are hitting these two parallel plate in a parallel hot plate in a equally and uniformly way. So, that every plate has having the height flux q 0, that means minus k del t del x is equal to q 0, which is boundary condition, and the bottom plate also the same heat flux, which is basically q 0. Now, this hot plate, between this hot plate the space is called the micro channel. So, this through this channel fluid is flowing and it is getting heated, and we are trying to find out the temperature profile that T x z, x is the that direction that which is called that what you call transverse direction, and z is the axial direction. So, and x equal to 0 is the center line, and as you see that that cell is basically that del x is the thickness. We are considering one cell which has the del x and length of delta z in the figure B. So, that cell we are considering for the heat balance. Now, okay. Oh, it has come, no? Right.
White page take click করুন,
white place take. Okay. Sorry.
Start.
Then this will go, and that I have to put that, right. Oh, it is not going. Yeah. It's good. Oh.
Sir, arrow symbol is there in the bar, see.
Arrow
symbol.
Arrow symbol.
ওটা click করুন স্যার, তাহলে ওটা you will go for the next slide.
Okay.
Yeah.
Oh, arrow symbol. Oh, আচ্ছা আচ্ছা ভুলে গেছি. Okay. So, here what we see that we can calculate the Nusselt number for this particular example for different cases. Two cases we have considered. One case is called that how when that velocity is constant throughout the channel cross section, which is called that potential flow, or maybe called that there is no viscosity effect. Another case we have considered, that is called that your parabolic profile throughout the cross section, and we can see that this parabolic profile has the effect of viscosity. Two cases, one is first case is the effect of viscosity, no effect of viscosity, second case is the effect of viscosity. And you can check that this is the, before writing that cell balance, we have to assume certain things, because problem is so complex. Certain assumption will help you to find out some equation, like we see that steady state we have to assume, because although everything is dynamic in nature, but to simplify the situation we can use that quasi steady state. And next thing, that is your incompressible flow. I will show that how it is that assumption is helping you out to find out the equation. And next thing, that end effect is neglected, where that end effect by assuming that if your B that means cross sectional width that B is basically that distance between two plates, distance between center line and the two plate that B will be very small compared to width and length as you see in the figure, and we are ignoring that heat flux along z direction. That will help you out to simplify the problem and to derive the equation. That means, that heat flux along z direction, you will see that if it is a long bar, you can neglect this heat flux or long channel, you can neglect that heat flux along z direction. So, and obviously that since heat flux is as giving the boundary condition in transverse direction. So, heat flux along z direction will be very negligible compared to the transverse direction. Now, two, three assumptions are there more. The viscous dissipation, there is energy due to the viscous dissipation that has been neglected, because this is Newtonian fluid, we have considered the water flow also. Second thing that that thermal conductivity or thermal property is not changing too much with the temperature, because all these assumptions will help you out to find out that equation which we like to have. So, that for cell balance, as you see that we consider rate of thermal energy balance and rate of thermal energy balance by conduction at x equal to x. As you look at the cell, rate of thermal energy out by conduction at x equal to x plus delta x. Third part is that rate of thermal energy in by convection along z direction and rate of thermal energy out by convection due to bulk flow. The third and fourth contribution due to the bulk flow, that the convective part that we have to consider, because velocity bulk flow is there. So, we have to consider the bulk transport of heat. That now, all these four component will give you this conservation principle, that rate of thermal energy in out by conduction, rate of thermal energy in out by convection, and this all in out that is equal to 0, the in minus out equal to 0, which is basically the principle of thermal energy or conservation or any energy conservation. Here we derive based on this thing, we can derive the this partial differential equation applying the that Fourier's law. Fourier's law, as you see that, and we apply the compressibility continuity equation to derive the equation which is called that V z del t del z equal to alpha into del 2 t del x 2. This governing equation will help you out to find the variation of temperature along x axis and z axis. Now, this is not complete equation, we have to give the boundary condition for this equation to derive the complete solution. As you see that equation, it is the first order derivative with respect to z and second order derivative with respect to x. So, we have to have three boundary condition that we have been put, that we have previously described, that one boundary condition 1 which is basically that T 0 at z equal to 0, boundary condition 2a which is basically the heat flux at x equal to x b, and boundary condition 3a which is basically the heat flux at x equal to minus b, and this heat flux has been connected with that Fourier law, and this boundary condition 1 is known as the Dirichlet boundary condition, second one is called the Newman boundary condition, third one is called the that is also Newman boundary condition. So, all these 3 boundary conditions will help to find the solution, but this solution to be in the general, to find the general solution, we have to define certain dimensionless quantity, which is called the dimensionless temperature theta, and that zeta and this eta. So, zeta for that your x direction, eta for your z direction. So, that dimensionless quantity will help you to find out the general solution, and which is basically substituted to find out that del theta del eta is equal to del 2 theta del zeta 2. So, and that all the boundary condition has been reduced to that dimensionless quantity, dimensionless equation. So, dimensional equation has been reduced to dimensionless equation along with its boundary condition, because there is use of dimensionless quantity, as you know that it will help you to find out that solution very readily. Now, we can use that asymptotic solution. We can propose on an asymptotic solution that will facilitate that find the solution of the PD of that dimensionless form. We use that this asymptotic solution, which is called the theta is equal to CO0 eta plus f that psi zeta, and this has been this proposed based on that based on the assumption that we have to have that fully developed region at certain length, for which that z has to be, the eta has to be large, and this eta will be that theta, this theta solution will be substituted in that PD that we have in the PD dimensionless form, and we can find out this solution here. But one problem with this asymptotic solution, as I go back, that this first first boundary condition BC1b cannot be satisfied by this asymptotic solution which is given here. So, what we have to do is that we have to modify that boundary condition 1b as you see to boundary condition 1c. That boundary condition is modified, that means BC1b is modified to BC1c based on that overall heat balance at the length of eta. So, so we consider the overall heat balance, for which we have to give another boundary condition which can be satisfied by that asymptotic solution. So, based on that boundary condition, all these 3 boundary condition, we can derive this equation which is given by this theta is equal to C0 eta plus C0 zeta square by 2 plus C1 zeta plus C2, which is that will be C2, and this C2 is basically all these 3 constant we can found by putting the boundary condition 2 and that your 2 B 2C and BC 1C. So, from there we can find that ultimate solution is which is called that eta plus zeta square by 2 minus 1 by 6. This solution can be taken as a tool for finding the Nusselt number for that fluid heating. So, for that we have to define the Nusselt number. As you see that Nusselt number, that we always define that temperature gradient at the surface due to conduction divided by temperature gradient in the bulk due to the convection. So, based on this definition, we have calculated all this gradient from the equation, from the solution that we have. From this solution means if I look at that theta solution that we have, we can derive all this derivative all this bulk temperature and surface temperature from that solution, then we can got this, and as you see that bulk temperature, which is basically that depending on the area of the or area of cross section of the channel, and integration of this temperature over the cross section, which is basically the definition of bulk temperature. Now, as you see that here this Nusselt number can be defined as 12. So, for this case where the velocity is constant throughout the cross section. Now, I can switch to that things this where the your velocity is changing parabolically over the cross section, and we can use this velocity profile, as you see that laminar flow profile, which is parabolic in nature, which is that problem is there in the Barden-Stewart. This problem will tell you that what is the velocity profile across the cross section in that slit, that velocity profile we have used, and eta has been modified to that previously that eta was defined dimensionless length, yes, that length, that has been modified to that V has been replaced by V max, and V max we have defined based on the pressure drop. So, now this in this case we see that differential equation has been modified to 1 minus zeta square del theta del eta and equal to C 0 1 minus zeta square. So, this equation has been once again solved based on the boundary condition. The all this boundary condition, as you see that this boundary condition, one boundary condition 1 C B C 1 C boundary condition has been modified also in this case, that if you look at that another extra term 1 minus zeta square is added. So, you will find that this modified boundary condition, the solution is like the theta is equal to 3 by 2 plus 3 by 2 zeta square by 2 minus zeta square by 12 minus 39 by 280. So, so based on this theta profile, we can calculate all this bulk temperature and surface temperature, and for that case with the similar definition of that Nusselt number, we can find that Nusselt number in this case 12. If I go back, if you check that your previous case, that where the Nusselt number is equal to 12, where the velocity profile is flat, I mean there is no viscosity effect, but Nusselt number is 12. Here in this case, if you look at that Nusselt number is basically 10, which is decreasing in this case when there is a viscosity effect. So, that means what is saying that when there is a viscosity effect, it will increase the thickness of boundary layer of thermal boundary layer and hydrodynamic boundary layer. That thickness increase will decrease the your Nusselt number. Obviously, as you see that potential flow has a higher Nusselt number compared to that laminar flow. So, this this example will tell that how that heat transfer is affected by the velocity profile or viscosity effect, and at last I should whatever we see that is basically due to I should appreciate my teacher and my students for helping me to understand the physics of this problem. So, I should I think it's a nice video room also IIT Kharagpur. So, I am happy to see this also.